Most people probably think that the night sky is pretty empty. When we look up at the stars, they seem scattered randomly across the inky blackness. And it's true there are billions of light years between most of them. But don't be fooled by that cosmic quiet period. There was a time when the universe was dead silent, or as silent as it gets when you're made entirely of energy. That was a long time ago, 400,000 years before the first stars flickered into existence. But it's not too late to get some sweet revenge, so let's hear it for the Big Bang. We know that the universe began with the Big Bang because that S where all of the matter and energy in the modern universe came from. But the universe didn't start off as the universe we live in today. Oh, no? It started off a lot smaller and a lot hotter, so hot that no atoms could exist. All of the stuff we're familiar with today, like galaxies, stars, and planets, would have been completely unrecognizable. In fact, the first few minutes after the Big Bang, the only element in existence was hydrogen. And instead of forming cool things like stars and planets, the universe just expanded and cooled. This period in the early life of the cosmos has been dubbed the Dark Ages because even though there was plenty of energy floating around, there wasn't any light to be seen. You see, light can only exist once the energy has cooled off enough to form those familiar waves of oscillating electric and magnetic fields. But this primordial energy was far too hot to settle down and form light. So, for millions of years, the universe was a dark, silent place filled only with cooling hydrogen gas. This might sound like an amazing time to get some uninterrupted shut-eye, but unfortunately, even sleep wouldn't have helped because your eyes wouldn't have worked either. There was no oxygen around, so your lungs wouldn't work either. In fact, nothing would work because nothing existed yet. There were no protons, neutrons, or electrons. All we had was a hot soup of elementary particles zooming around. Eventually, these particles started combining to form the nuclei of the simplest atom, hydrogen. Then the universe had to wait another 380,000 years for the energy to cool enough for electrons to be captured by those nuclei, and the first good old-fashioned atoms were born. But even once those atoms formed, the universe was still stuck in its dark and silent phase because there was no light. To make light, you need a source of energy, something giving off photons, which are the quantum of light. But there were no stars or galaxies to be found in this dead universe. Not yet anyway. The universe needed a light switch to be flipped. It needed something to kickstart the formation of stars and galaxies and rayonize the neutral hydrogen that permeated the cosmos. And that is when the first stars finally ignited. The exact details of how that happened are still being explored by astronomers, but the end result was that the universe went from being dark and silent to being filled with light and buzzing with activity. In other words, the cosmic quiet period came to an end. The universe was never truly empty, but now it was very different than it had been before. In fact, understanding what happened during the cosmic quiet period and how it ended is helping astronomers map out the structure of the very first galaxies and learn more about our own galactic home. It is kind of crazy that we can learn about the very first structures in the universe by studying the light that passed through them over 13 billion years ago. But here's how we do it. Remember how I said the universe was filled with hydrogen gas during the cosmic quiet period? Well, it turns out that hydrogen gas will absorb certain frequencies of light. Specifically, there's one frequency that gets absorbed really easily. Hydrogen likes to soak up photons with wavelengths of about 21 centimeters. That makes sense. Atoms tend to act like little magnets because they have spinning electrons inside them. And those spins are quantized, meaning they can only be a certain amount, say north or south. But if a photon with the right energy hits an atom, it can flip the spin of that electron, and that's what happened with the hydrogen atoms in the early universe. Photons would bump into hydrogen atoms and flip their spins. There was one problem, though. Once that happened, the electrons would fall back down to their original spin state and release a photon. But that photon would go off in a random direction, so the first stars couldn't really do much to change the darkness of the universe because the photons they emitted were immediately lost in a sea of randomly bouncing photons. So if they wanted to shine a light into the darkness, they would have to emit photons with a very specific wavelength, a wavelength that was slightly longer than the 21 centimeter wavelength that hydrogen likes to eat up. If the stars could emit photons with wavelengths around 21.6 centimeters, then they could punch through the fog of the 21 centimeter background radiation that blanketed the universe. Today, we can detect this radiation, this faint echo of the cosmic quiet period, in the microwave part of the electromagnetic spectrum. It's called the cosmic microwave background. And while it's incredibly useful for learning about the early universe, it also poses a problem for modern telescopes, because that 21 centimeters wavelength is the same as the radio waves that cell phones use. So if you want to take a picture of something in space with a radio telescope, you've got a whole bunch of static to sift through. But that shouldn't surprise you, since the early universe was the source of that static. But there are telescopes that are designed to see beyond the static. One such telescope is the 100-meter array of low-frequency radio telescopes called LOFAR, which is located in the Netherlands and eastern England. LOFAR was built specifically to pick out the faint signal of the cosmic microwave background from the noise of modern society. And in 2017, it accomplished something that hadn't been done before. Using 7 of its radio telescopes, LOFAR created an image of the sky at 21.6 centimeters and revealed a faint glow. The glow corresponded closely with the location of the cosmic microwave background radiation, proving that the photons punching through the fog of the universe were coming from all directions. That meant the universe itself was ionized, meaning the first stars had succeeded in making the universe more like the universe we live in today. But we still don't know exactly what those first stars were like, or how they managed to emit photons with the correct wavelength to pierce through the hydrogen gas. One idea is that these special stars were extremely massive and very hot, around 50 times the mass of our sun, and burning through their fuel at a similar rate. These stars would have burned out within a few million years, leaving behind clouds of iron and helium. And as more and more stars ignited, the metal-rich dust would have condensed into the first galaxies. Another idea is that it wasn't the stars themselves that produced the ionizing radiation, but rather the supernovae that marked their deaths. Either way, the light that finally pierced the darkness of the cosmic quiet period sparked the creation of everything we see around us today. And now we're working on creating light ourselves. Right now, scientists are working on several projects to create artificial light sources that could help solve the problem of the 21 centimeter background radiation. One project, called the Square Kilometer Array, will use dozens of radio telescopes across South Africa and Australia to create an image of the sky 10 times faster than any telescope has done before. By imaging the sky faster, it can also compensate for the interference of incoming radio waves and cut through the noise. This will allow it to study the structure of the early universe in unprecedented detail. And hopefully it will answer some outstanding questions about the very first galaxies in the universe. We'll just have to wait and see what light we can shed on the cosmic quiet period. But one thing's for sure, if you want to learn more about the amazing universe we inhabit, thanks for watching this SCI Show video, and thanks to our President of Science for helping us make it.